Okay, let's talk about one of your favorite topics, the titration curve. What we're going to do here is we're looking at the titration of a 40 milliliter sample of 0.100 molar propanoic acid is titrated with 0.200 molar sodium hydroxide. So just to review, can't help myself, propanoic acid, one of our organic acids. Prop means 3. It's an acid, so it's got a carboxylic acid group on the end. There is propanoic acid. Again, if we want to be most complete, we could fill in all the hydrogens. I hope I don't need to do that for you. These 5 hydrogens are all connected to carbon. They are not the acidic hydrogens. They refer to these 5. Okay. This hydrogen on the other end is the acidic hydrogen. All right. For our purposes, we're going to represent that monoprotic acid as our old friend Ha, or HA, being titrated by a strong base. Strong base, sodium hydroxide, sodium ion, hydroxide ion. Sodium ion is a spectator. We're not going to pay any attention to that. It's the hydroxide ion that we're interested in. Hydroxide ion is a strong base. All right. What's in the flask? What's in the burette? We've got a titration. Always kind of nice to make sure you can orient yourself. What's in the burette? What's in the flask? In the burette is the 0.200 molar sodium hydroxide. It's what we call the titrant, to use a fancy word. In our case here, the titrant is the strong base, 0.200 molar sodium hydroxide. In the flask, we've got a pH meter as well. In the flask, we've got the 0.100 molar of the weak acid HA, and we also know that we're starting with 40 milliliters of that acid, okay? So acid is in the flask, titrant is in the burette, and now what we're going to do is we're going to add, in a controlled fashion, because we've got this nice little stopcock here, this little valve, we're going to add controlled amounts of the base to the acid and want to predict what the pH of the solution will be. All right, a couple of things. So first of all, orienting ourselves. Always helps to draw a picture. Secondly, what is the equivalence point? The equivalence point is a important point. The equivalence point is the point at which we've added just enough acid, added just enough acid, enough volume of, a volume of OH minus, the sodium hydroxide solution, to just react with all of the HA. Well, actually, before we did that, we should have written down what the titration reaction in our flask. We've got the weak acid in the flask. 40 milliliters, 0.100 molar. We're adding to that from the burette the hydroxide. It's in the burette. Its concentration is 0.200 molar. It's twice as concentrated as the acid. The titration reaction, acid-base reaction, our weak acid donates a hydrogen ion to the strong base. The result is that we form the conjugate base and some water. Okay, so there's the what we call the titration reaction. This is what's happening as we add base to the acid. Okay, now the equivalence point is a special point where we've added just enough of the base to react with all the acid. So what is the equivalence point? How many milliliters of sodium hydroxide solution do I need to just react with 40 milliliters of my HA solution? I know the HA solution contains 0.100 millimoles. I'm going to use millimoles because I don't want to have to convert to liters per milliliter. Know that a millimole per milliliter is the same as a mole per liter. Milliliters of HA cancel milliliters of HA. That tells me how many millimoles I have swimming around in my flask. From the reaction, I know that 1 millimole, I know it sounds funny to say a millimole, 1 millimole of hydroxide reacts with 1 millimole of HA. Cancels. I now know that my sodium hydroxide, for every milliliter of the hydroxide ion solution, I have what? I have 0.200 millimoles of OH minus, right? Millimoles and mole candidates H minus cancel. If we do that calculation, we find out that the equivalence point volume is going to be 20 milliliters. This is an important benchmark. We know that any volume before 20 puts us before the equivalence point. We know that any volume of sodium hydroxide added after 20 puts us into the region where all of the acid has been used up and we have just excess sodium hydroxide. If we've added exactly 20 milliliters, we know we're at the equivalence point. And finally, if we haven't added any sodium hydroxide, we know we haven't started the titration, we just have a weak acid problem. So knowing the equivalence point really orients you in terms of what you're doing at different points during the titration. I can't emphasize that enough, that if you're not asked for the equivalence point, you still want to calculate the equivalence point. Now, a couple other things we need to know about our acid. Here's our acid, HA. Okay, it has a pKa of 4.87, which means its Ka is equal to 10 to the minus 4.87. Don't be intimidated by pKa's. Remember, pKa is just a very compact way of communicating the Ka. pKa is equal to the negative log of Ka, just like pH is the negative log of the hydrogen ion concentration. Okay? Good. So let's start doing some work. So first of all, what is the pH? So we'll call this letter A. Okay? What is the pH of the solution before adding any sodium hydroxide? So what is the initial pH of the solution? All right? So remember, before we've added any sodium hydroxide, all we have is a 10th molar solution of a propanoic acid. This is just a weak acid. We have a weak acid. We can do weak acid calculations. We've been doing lots of those. One more time. HA is our weak acid. HA is going to ionize and come to equilibrium, forming some H plus and A minus. We know that the Ka for this reaction is 10 raised to the minus 4.87, which is equal to the concentration of the H plus, concentration of A minus, over HA. All right, so maybe you're familiar with the ice table. I hope so. ICE. Initially, we have a 10th molar solution of the acid. We're going to assume that we have 0 H plus and 0 A minus. System comes to equilibrium by moving to the right. X is the amount of HA that ionizes, X is the amount of H plus that's produced, X is the amount of A minus that's produced. At equilibrium, therefore, our concentration of HA is its initial concentration minus X, concentration of H plus is X, concentration of A minus is X. You know the routine. We're going to plug those X's into their appropriate concentrations up here. So X is the hydrogen ion concentration, X is also the A minus concentration, 0.100 minus X is the HA concentration. We know that all has to be equal to 10 to the minus 4.87. We assume X is much, much less than 0.10, so we can make the assumption that the change in the concentration of the weak acid is insignificant, so that simplifies the math for us. 8 squared over 0.100 equals 10 to the minus 4.87, or X equals, if we solve for X here, X equals 1.16 times 10 to the minus third molar. Again, that is our hydrogen ion concentration. The pH of the solution is the negative log of that, and therefore the negative log of that is going to be, excuse me, I've got it here somewhere. had calculated that ahead of time. Let me take a second here to calculate that. Negative log. Two point nine four. So the pH of the solution initially 2.94. So our initial pH point before we've added any sodium hydroxide pH is going to be 2.94. That makes sense. Weak acid, okay, not completely ionized, only a very small fraction is ionized. We're definitely producing some acid, but not a significant concentration of the acid. The pH is just a little less than 3. Again, remember, if this was a strong acid and it had a concentration of 0.1, pH would be 1. All right. Now, add 5 milliliters of NaOH. What is the pH? So, what's happened? Well, here's what's happened. Okay? Again, as the reaction proceeds, HA reacts with the OH minus to form A minus plus HA. Okay? The concentration of the HA goes down as it reacts with the sodium hydroxide. The concentration of the A minus goes up. This happens all along the way until we get to the equivalence point. Now, there are a variety of ways to solve this. Here's the way I like to solve these problems. Let's think about what percentage of the way we are towards the equivalence point. I've added 5 milliliters. I know the equivalence point is at 20 milliliters. So percentage to equivalence point equals 5 out of 20, or at this point, we're 25%, or 0.25 to the equivalence point. What does that mean? Well, that means that the HA concentration has decreased to 0.75 relatively of its original concentration. The A minus has increased to 0.25 of its original concentration. We don't need to know the actual concentrations, we just need to know the relative ratios of the two. We're going to use our favorite equation, the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the conjugate acid. We plug in, pH is equal to, we said the pKa for our acid was 4.87. Log of the relative A minus concentration is 0.25. Relative concentration of the HA is 0.75. There's our relative ratio. We do the calculation, and the pH is going to be 4.39. Okay, the pH is 4.39. Okay, the acid concentration is still greater than the base concentration. We're only 25% to the titration. Therefore, we're not surprised that the pH is below the pKa. Okay, good. Part C. Play the same game. Now we're going to add 7.5 milliliters of NaOH. We want to know what the pH is. Pretty straightforward. Where are we now? We are now percentage to equivalence point equals 7.5 over 20. We are 60, excuse me. We are 62.5%, 0.63. Excuse me. We are 37. I'm sorry. We are 37.5% to the equivalence point. Therefore, the HA concentration has decreased to a relative 0.625. The A minus concentration has increased to a relative 0.375. Again, what are we going to do? We're just going to take those relative percentages, plug them into our Henderson-Hasselbalch equation. pH equals 4.87 plus the log of the base goes on the top. The relative acid concentration goes on the bottom. And bingo, we calculate that the pH at 7.5 milliliters is 4.65. All right, Good. The pH is increased. We're adding base. That makes sense. Notice the pH is not increasing dramatically. We're making a buffer. Okay? Our buffer is getting increasingly good. Remember, a good buffer, best buffer, has equal concentrations of both the acid and the base. As this titration is occurring, the acid concentration is decreasing. The base concentration is increasing. Okay? So if you notice what's happening here, our titration reaction is converting the conjugate acid, in this case the propanoic acid, into the propanoate ion as we proceed in the titration. So that ratio is constantly changing. All right, letter D. What's happening at 10 milliliters? What's the pH? Okay. At 10 milliliters, we're at a very special point. At 10 milliliters, we are exactly halfway to the equivalence point. We sometimes call this the midpoint of the titration. Okay, so at 10 milliliters, we are 50% to the equivalence point. What does that mean? It ends up being a very special point. At this point, the concentration of HA has been reduced to 50% or 0.50 of its original concentration. The A minus has been increased to 0.50 of the original concentration of the acid. And therefore, the concentrations are the same. pH, again, is going to be equal to the pKa 4.87 plus the log of 0.5 on the top for the base concentration, 0.50 on the bottom for the acid concentration. Notice that ratio is 1. We have our best buffer. Log of 1 is 0. pH equals pKa. Hardly any calculation required there. So recognizing that midpoint, pH equals to pKa. All right, continue on. A little bit more exercise. This kid's pretty old after a while. Suppose we're at 15, let's go to 15 milliliters added. What's the pH now? Okay, I hope everybody can say at 15 milliliters, we are what, 15 out of 20, or we are 75% to the equivalence point. What does that mean? That means the relative concentration of the A minus now is 75% of the original concentration of the HA. The HA concentration has decreased to 0.25 of its original concentration. One more time, pH equals 4.87 plus the log of the A minus concentration, 0.75 over 0.25. Okay. Notice now that the base concentration is higher than the acid concentration. The pH at this point is going to be, I thought I had it somewhere here, log of 3. Again, let me stop and do a quick calculation. pH is going to be 5.28. Okay, notice that this is just really sort of the opposite situation of what we saw previously. When we were at the 25% point, notice at the 25% point the ratio was 1 to 3 of base to conjugate acid. When we've gotten to the 75% point, the other side of the pKa, the other side of the midpoint, the ratio now has flipped. The ratio now is equal to 3 over 1. Okay, so there's a nice symmetry here. If you understand that symmetry, you've got a good connection, good feeling for pH titration. Okay, good. So in that region before the equivalence point, so after adding hydroxide But before the equivalence point, we really are working with buffers. And when you're working with buffers, there's no more convenient way to work when working with buffers than using this classic form of the equilibrium constant expression, pH equals pKa plus the log of the base concentration over the conjugate acid concentration. Okay, so that's the chemistry that's happening as long as after we've added a little bit of the acid, the base, and before we got to the equivalence point. Okay, so now we're at the equivalence point. The equivalence point, 20 milliliters of sodium hydroxide added. What's happened? Well, again, to re-emphasize what the equivalence point is, after we've added 20 milliliters of sodium hydroxide, we've added enough sodium hydroxide to completely convert all of our HA into the A-. So, at this special point, and this is just one point on the titration curve, the A- is controlling the pH of the solution. All right? So, we've got a weak base, A- reacting with water. It's going to form some HA plus OH minus. The Kb for this base is equal to the Kw divided by Ka. Kw is 10 to the minus 14th at 25 degrees C. Our Ka was 10 to the minus 4.87. So the Kb here is equal to 7.4 times 10 to the minus 10th. Again, relatively weak base. Again, the strength of the base and the strength of the acid are inversely related to each other. The stronger the acid member of the conjugate pair, the weaker the base member of the conjugate pair. All right, we've got a weak base problem. Now, careful. What's my initial concentration of the base? Before I do my ice table, okay? I started out with how many, all of the acid was converted to its conjugate base. So the original millimoles of acid are going to be the original 40 mils that I started with, times its concentration, divided by the 40 mils of volume that I started with, plus the 20 mils that I added. So if I do that calculation, the initial concentration of my A- is going to be 2/3 of its original concentration. Okay? That's a point that people often miss. So now if I set up my ice table, A- reacts with water to go to HA plus hydroxide. My initial concentration, 0, 0, minus X plus X plus X at equilibrium. I've got 0.0667 minus X. I've got X and I've got X. I know the Kb is equal to the concentration of HA, concentration of OH minus, divided by A minus. I know that's all equal to 7.4 times 10 to the minus 10th. Plug in X, 0.0667 minus X is equal to 7.4 times 10 to the minus 10th. Again, we'll take our shortcut here, our assumption that X is insignificant relative to 0.0667. This simplifies to being X squared over 0.0667 equals 7.4 times 10 to the minus 10th. When you solve for X is going to be, thought I had calculated that ahead of time. Let me take a peek here. Sorry about that. X is going to be 7.03 times 10 to the minus 6. 7.0 times 10 to the minus 6. And remember, that is the hydroxide ion concentration The POH is going to be the negative log of that. Negative log of that is 5.15. The pH is going to be 8.85. All right, notice what happens here. The pH makes a huge jump in that small jump from 15 milliliters to 20 milliliters. The solution has no buffering capacity. The pH of the solution is determined by the conjugate base. Okay, so a rule of thumb, equivalence point for a weak acid strong base titration is always basic, because you've created a weak base at the equivalence point. All right, let's wrap this up. Now we're beyond the equivalence point. Let's say we've added 22.5 milliliters. So now part G, we've added 22.5 milliliters. Now we're past the equivalence point. And now the situation that we have is we have just excess sodium hydroxide. Sodium hydroxide has nothing to react with. Here's an easy way to work this problem. We know that the first 20 milliliters went to the reaction, so really we have 2.5 milliliters of excess sodium hydroxide. I hope you know what I mean by that. That 2.5 milliliters has nothing to react with, so it's just going to build up in the solution. So the concentration of hydroxide in this solution is going to be 2.5 milliliters times the concentration of the base, which is 0.2 molar, divided by the total volume of the solution. We started with 40 milliliters of acid. We've added 22.5 milliliters of base. Therefore, my concentration of hydroxide is 0.008 molar. The POH is equal to 2.10. The pH, therefore, is 11.90. Okay, very basic. Do one more. H, let's suppose we've added 25 milliliters of sodium hydroxide. We want to know what is the pH. Again, now what do we have? We have 5 milliliters of excess NaOH. What's the concentration of hydroxide? It's the 5 milliliters in excess times the concentration divided by the total volume, the 40 that we started with, plus the 25 that we added. The hydroxide ion concentration, therefore, in the solution, the excess hydroxide ion concentration is equal to 0.0154. The POH is equal to 1.81, and the pH is a whopping 12.19. Okay? So, titration curves. All right? Hopefully that made a little bit of sense. As we scroll to the bottom of the page here, I think I've got a titration curve down here somewhere, didn't I? Oops, I don't. Thought I did. Let me grab a titration curve for you. I'm going to jump backwards here just for a second. Actually, I think we'll just end it there. All right, I'll put a titration curve in the next video. All right, I hope that all makes some sense. 4 regions in a pH titration. We've got the initial pH. That's a weak acid problem. We've got what we call the buffer region. That's before we get to the equivalence point. Then we've got that big transition point. We've got the equivalence point. So this is our buffer region. Over here, HA is being converted to A minus. The midpoint is an important point. pH equals pKa. Equivalence point, A minus plus H2O is producing HA plus hydroxide. That's a weak base problem. And then finally, beyond the equivalence point, we have excess hydroxide. All right.